Good afternoon, everyone. My name is Nikhila Patil. I am the PhD scholar from IIT Roorkee. So I'll be presenting our work, Aluminium Dope, Zinc Oxide, and Silver Nanowire Composite Ink for CO2 gas sensing. So we know that CO2 is a significant greenhouse gas, and monitoring CO2 in an enclosed space is very important. Okay. So moving further, the motivation behind this was if we are in an enclosed space with number of people increasing more and more coming inside and the space becoming less and less, then the concentration of CO2 will be more. So monitoring it continuously is very important. But using the traditional gas sensors, we know that these traditional gas sensors operate at very high temperature, okay, and then they provide external heating also, require external heating also, and this gives that rise to the power consumption, more power consumption, okay, and these are not suitable for a low power portable electronics and wearable devices. So our objective was to design or develop a miniaturized CO2 gas sensor using printed electronics so that making it very much flexible and a smaller size device that can be used efficiently working at room temperature so that it will be operated at a very low power. Okay, so we utilized aluminum dope, zinc oxide, and silver nanowire composite ink, which will operate efficiently at room temperature and using a very latest technique, which is a 3D printing, that is a direct printing technique. This ensures that we get a consistently uniform printed layer using a printed screen print sensor. So I would like to summarize our contribution. Here is an image showing us that how we started with and ended with the gas sensor. So basically we synthesized first the aluminum dope zinc oxide, okay, and then added silver nanowires to it to make a composite ink, and then we printed this using and directing writing technique. Okay, so we have printed both the interdigitated electrodes using a DIW writing technique and also the film using the DIW writing technique. So here you can see that the silver nanowires incorporated into the azoto film, and then we tested it as a gas sensor. So this worked efficiently, giving us a small miniaturized CO2 gas sensor. This is in short the summary of our contribution. So let's start with what exactly we did. So we started with preparing first the azoto nanorods. So azoto nanorods, we used a solution-based approach where first we synthesized the nanorods, and these nanorods were then mixed with the silver nanowires. But we also not purchased the silver nanowires, but we synthesized the silver nanowires using the polyol method. So these two solutions were mixed in a proper ratio and we got a final optimized ink. So we optimized the azoto concentration also, that is 28% azoto nanorod in a dispersion, plus our Ag nanowires which we synthesized into an optimized ink. So we adjusted the ratios of azoto and Ag nanowires to get that ink. That will be helpful for the gas sensing. So we did some characterization, structural and morphological characterization, showing us the incorporation of the Ag nanowires, that is the phase purity also, and clearly showing us the nanowires and the nanorods. So here at the bottom of the slide, you can see these are the azoto nanorods, only synthesized, that is in the powder form. And after dispersion, you can see that when we are adding the silver nanowires and the silver nanorods. So this is the optimized ink, SCM of the optimized ink. Further, you can see that this is the interdigitated electrode which is printed by using the directing writing technique. And this is how when the ink is also printed using the directing writing technique. So this is a two-layer printed ink, okay? And the sensor dimension which we have used is approximately 21 to 12 mm sensor. Okay, so the active area, you can see that this is the active area which is used for gas sensing. So if I go further, this is the experimental setup where we use a gas testing chamber. Okay, it is a fixed volume chamber, and we purge a target gas using a mass flow meter and connect it to a source meter, giving us the performance. So with this azoto AG Nanowire Composite Nano Ink. So when we burst air or in air, what happens is that the oxygen gets absorbed onto this sensing layer and the resistance of the device increases because it forms a depletion layer. But when the target gas is pushed over it, what happens is that the electrons are released because of the absorbed oxygen which is there already onto the sensor, and when CO2 gas flows over it. That's why the resistance of the device decreases. The AG nanowires helps to form the Schottky junction with the AZO, which enhances the charge transfer and increases the efficiency of our sensing device. That's why our developed sensor was more efficient for sensing CO2 gas at a very low concentration also. So here is the testing result which you can see of the AZO 28%. So we developed 10 weight percent also and 28% and 38%. So three different concentrations we have tested for CO2. From that, 28% showed us a stable and repeatable result as compared to the 10 and the 38%. So here you can see that the response we got as a fast response is 19 seconds and the recovery of 36 seconds. And the repeatability of the 28% is far much better as compared to the 10 and the 38%. Moving further, here you can see that the sensitivity of the sensor which we got is 32% at 400 ppm, and the range for which we checked the gas sensor was 100 to 400 ppm. So the lowest percent or LOD for the CO2 gas sensor which we got is 24 ppm. And one thing which I want to tell that is this sensor operates at a lowest voltage of 1 volt. So that is very important because at that voltage that is low power consumption and giving us a effective output. So to summarize our work is that we developed a miniaturized printed CO2 gas sensor using a directing writing technique which shows a faster and more sensitive response as compared to the traditional CO2 sensors, which is low cost and can be used for scalable fabrication. That is, you can print it on a larger area also. You can use different substrates. It can be a flexible substrate. It can be a rigid substrate, anything. And also we synthesized all these things, that is from the sensing there to the IDE, everything. So we got fast response, higher sensitivity and good repeatability. So this can be a promising sensor for real-time environmental and industrial applications. Thank you. Thank you.